fear it. Until they understand it.
This design is the result of a mathematical breakthrough in the face of a crisis. A year earlier, the first reactor-bred plutonium samples began to arrive at Los Alamos. In a Forest Service cabin in Pajarito Canyon, away from the main laboratory to avoid stray radiation, the scientists began counting alpha particle emissions from these new samples. Up until that point, only microgram quantities of plutonium had existed anywhere on the planet. The tiny samples the scientists had were created in the Berkeley cyclotron. It didn't take long for them to realize that there was something terribly wrong with these new larger samples from the X-10 nuclear reactor in Oak Ridge, Tennessee. A 20 microgram sample of the cyclotron-generated plutonium would register around 1 count per month. These new slightly larger samples were wildly different, registering 8 counts in just the first 3 days of measurement. The implications of these numbers were catastrophic for the Los Alamos project. Oppenheimer called an emergency meeting. The gun-type bomb design that most of the lab's hundreds of scientists had been developing was not going to work. The design was supposed to work by firing one mass of plutonium into another, rapidly forming a critical mass. Plutonium is otherworldly. As soon as you have enough of it in one lump, a critical mass, it's basically impossible to keep it from exploding. A single-strain neutron is all that's required to set off the nuclear chain reaction that detonates the bomb. The alpha particle emissions these scientists were measuring are a result of the spontaneous splitting of unstable plutonium atoms. These fission reactions are the same mechanism that drives the bomb. They release neutrons that are capable of triggering detonation. The higher spontaneous fission rate meant that the gun-type bomb simply could not bring the two plutonium masses together fast enough. A maximum muzzle velocity around 1,000 meters a second means that it would take around 100 microseconds to join the two plutonium masses. A spontaneous fission would likely trigger a pre-detonation before the mass was fully assembled, making the bomb a billion-dollar dud. Oppenheimer proposed a risky way forward. A small group of scientists at Los Alamos, led by Seth Nettermeyer, had been quietly working on an entirely different way to build the bomb. It turns out that adding masses together is not the only way to reach criticality in plutonium. The growth rate of the neutron chain reaction that drives the bomb depends on overall mass, but also density. If a subcritical mass of plutonium could be rapidly squeezed to a higher density, it could reach criticality. To squish a plutonium mass in microseconds, Nettermeyer's group was developing an implosion bomb design. The idea was to create a controlled explosion around the mass inside a rigid container, directing the force inward and squeezing the plutonium until it reached criticality. However, early experiments were not going well. Using steel to simulate the plutonium mass, Nettermeyer's group would surround the mass with TNT inside of a cylindrical container, and ignite the TNT from multiple points. Iterating through various designs, they would invariably end up with mangled and twisted pieces of steel by the force of the explosion. The explosion wasn't symmetric enough to compress their masses. When hearing Nettermeyer's approach, the Los Alamos scientists compared it to squeezing water in your hand and expecting it not to squirt out. During Nettermeyer's presentation, Richard Feynman is reported as raising his hand from the back row and simply announcing that it stinks. Months before the crisis, with brilliant strategic foresight, Oppenheimer reached out to the genius mathematician John von Neumann to help with the implosion bomb. Always have a backup. Reviewing the problem and building on the work of others, von Neumann proposed a brilliant new design. The detonation waves of each of Nettermeyer's ignition points propagate in spherical wavefronts. The problem is that when these wavefronts converge on the mass, they don't apply even pressure all the way around, resulting in parts of the mass squirting out as it liquefies, not overall compression. Von Neumann saw a way to redesign the explosives, such that the detonation waves from each ignition point would be shaped to match the spherical plutonium mass. Borrowing from optical lens design, von Neumann realized that he could shape the wavefronts using an arrangement of high and low velocity explosives. He divided the explosives into individual lenses, and within each lens placed a cone of low-velocity explosive inside of a region of high-velocity explosive. The key idea here is to slow down the more direct paths taken by the detonation wave by just the right amount so they arrive at the same time as the less direct paths. Mathematically, the total travel time between the ignition source and the mass should be equal for all paths. The exact cone shape can be computed by solving for cone height as a function of position and depends on the detonation wave velocity and the slow and fast materials. To make all this work in 3D, von Neumann basically designed a huge soccer ball, with pentagon and hexagon-shaped lenses fitting together in a 3D puzzle around the plutonium core. Oppenheimer knew that von Neumann's design would work in theory. However, he was all too aware of the huge engineering challenges in actually building this complex design. The geometrically complex 3D lenses would have to be formed from new types of high explosives. The lenses would need to be ignited with synchronized microsecond precision. Diagnostic equipment would need to be designed from scratch to determine if experiments were compressing the core as expected, and even the theory was not entirely sound. Von Neumann's design assumed that the detonation wave velocity was constant in a given material. Oppenheimer knew this was not true. Detonation wave velocity is nonlinear and non-local. It depends on the shape of the boundary and the overall scale of the lens. It would take the full force of the Los Alamos lab to solve these problems. Within 2 weeks, Oppenheimer completely reorganized the lab to work on implosion. Testing was a huge challenge. How could the scientists measure how symmetrically and quickly a given design compressed the core when the explosion was over in microseconds and destroyed the test material? The newly formed X and G divisions simultaneously pursued 7 different testing strategies. High-speed X-rays allowed the scientists to see inside the bomb as it imploded, capturing the density changes as the detonation wave propagated through the explosive. However, X-ray methods didn't give good visibility into the compression of the core itself, and could only provide a few snapshots as the bomb imploded. Robert Serber proposed a clever improvement. Instead of having an X-ray radiation source sending X-rays through the bomb, what about moving a radiation source into the core itself? Serber proposed placing a sample of radioactive lanthanum-140 inside of the core of the bomb. The gamma rays emitted by the lanthanum could be measured at multiple locations outside the bomb using ionization chambers, and plotted on oscilloscopes, giving continuous data instead of a few snapshots as the bomb imploded. As the core compressed, the higher material density would absorb more gamma rays, reducing the detected values. By comparing the various oscilloscope traces, the timing and symmetry of the core compression could be measured. Known as the Rala experiments, these tests provided some of the most reliable data to guide iteration on bomb designs. Actually running these tests was a different matter. The lanthanum sources emitted very unsafe levels of radiation. Serber commissioned 2 military tanks to protect scientists as they captured data. Each implosion would destroy the ionization chambers. And in the first test, Serber forgot to account for the fact that the entire forest would catch on fire, and the scientists had to flee the scene in their tanks. These tests revealed a myriad of problems with the bomb design. The firing of each lens was not well synchronized. Slight manufacturing differences between the explosive detonation wires connected to each lens led to problematic timing differences on the order of microseconds or more. Luis Alvarez led a redesign of the ignition system, switching from explosive wires to a new electrical detonator design, ultimately bringing synchronization within a few hundredths of a microsecond. Manufacturing explosive lenses presented a huge range of challenges. 3D complex molds had to be designed, and the high explosives were prone to cracks, bubbles, and other imperfections. Over an 18-month period, the lens production facility delivered over 20,000 lenses to test sites, with many times this number rejected due to poor quality. At the heart of many of these problems was a poor mathematical understanding of detonation wave hydrodynamics. No analytical solutions were known for the governing equations. Von Neumann proposed an iterative numerical approach to a Lagrangian formulation of the problem, where the bomb was modeled as a set of small masses connected by springs. For each time step, the position of each mass depends on its previous 2 positions, and the pressure on the mass a half step away in each direction. Starting with boundary conditions based on the lens shape and ignition source, the path of the detonation wave can be computed. This process is enormously time-consuming, and was initially performed at Los Alamos by groups of human computers using mechanical desk calculators, led by Richard Feynman, and was later performed on IBM punch card accounting machines. Von Neumann's methods were improved by other scientists, but were still limited in their predictive abilities, leaving a painfully slow iterative trial and error approach as the primary path to a working implosion design. Months of development led to hard-fought improvements, and by the summer of 1945, the Los Alamos scientists had a design that appeared to be capable of compressing the core quickly and symmetrically enough, although not all testing methods supported this conclusion. Testing the full device was set for the morning of the Potsdam Conference, potentially giving President Truman valuable information in his negotiations. At 5:29 a.m. on July 16, 1945, all of the Manhattan Project science, mathematics, and engineering came together in a blinding flash of light in the New Mexico desert, followed by the most violent explosion humans had ever created. equivalent to the detonation of 20,000 tons of TNT. Oppenheimer's gamble on the implosion bomb had paid off. Humanity now had the power to destroy itself.